In this video, we will discuss a topic that is central to rocket design and the flight of projectiles. This being the rocket's center of pressure and its location with regards to its center of gravity. First, we will use SpaceClaim to obtain our rocket center of gravity, and then we will use our CFD simulation conducted in Fluent to calculate the center of pressure in order to determine the rocket's stability. And finally, we will look at ways to obtain better performance in flight. In order to perform a center of pressure analysis, the rocket's nose will need to be pitched upwards, creating a slight angle of attack. This will produce an asymmetric force on the rocket, mimicking oscillation in flight. This will give us the ability to perform a more accurate center of pressure calculation. We will now return to SpaceClaim to obtain the center of gravity. Here we have our original geometry of the 2-diameter rocket. So first we will hide the enclosure. Now we can examine how to apply material properties to the rocket. Since we did not create separate sections or regions for our rocket, we will only have one material. If your geometry has several stages, sections, or materials, you will want to assign material properties to each section in order to obtain an accurate center of gravity. To assign material properties, first select the solid you would like to apply the properties to. Next, navigate to the Properties window in the bottom left-hand corner, and notice that the material is unassigned. By selecting this drop-down menu, we can select various material assignments. For our rocket, we will select titanium. Now navigate to the Measure tab and select the Mass Properties tool. Next, select the rocket. A table will appear with the various properties. Since the center of mass is the point through which gravity acts, we will want to copy this location as it will be our center of gravity. We can see here that a local origin for the rocket appears as the center of mass. In Fluent, we will plot points for center of gravity as well as center of pressure to visually understand where each point is located. We will now return to Fluent to calculate the center of pressure from our simulation. Fluent has the capability to calculate the center of pressure for us. To do this, navigate to the Results tab in the Reports section. Select Forces, and the Force Reports window will appear on the screen. We can see in the Options panel we have the ability to calculate the center of pressure. Select Center of Pressure, and then enter the coordinate value. In SpaceClaim, we set the tail of the rocket at the origin with the body of the rocket oriented along the y-axis. Since the flow is also along the y-axis, we can assume that the center of pressure will vary along the y-axis while being 0 or at least very close to 0 in the x and z axes. Now select the x coordinate and set the value to 0. If the exterior walls of the rocket are not already selected, do that at this time. Next, click Print, and the center of pressure location will be printed to the console window. We can see that with a coordinate of x equals 0, there's a very small, nearly 0 value for the z-coordinate. Now, we will set the z-coordinate equal to 0 to calculate the center of pressure in order to understand how this will affect the location. When we calculate this, we can see that the x and z coordinates are nearly 0, and the y coordinate is very close to the value when x was set to 0. Now, looking back at our center of gravity obtained in SpaceClaim, we can already tell that our center of pressure occurs between the center of gravity and nose. Therefore, the design will be unstable in flight. Nevertheless, we can still plot these 2 points to get a visual representation of the difference between the center of gravity and center of pressure. First, we will plot the center of pressure. Next, we will plot the center of gravity that we obtained from SpaceClaim. With this information, it is easy to see that the center of pressure is too far forward and that our geometry needs to be modified. In order to move the center of pressure behind the center of gravity, we could either attempt to modify the geometry, for example, shortening the overall length from the tail section, thereby moving the center of gravity forwards. Or we could also add tail fins in an effort to move the center of pressure rearwards to help stabilize our design. In order to verify our modified design approach, we would need to rerun our analysis in order to find the most stable geometry and rocket configuration. This concludes the External Aerodynamics Rocket Analysis video series.